This video is an overview of fluid mechanics, just to cover the important bits for competitive examinations, especially for state board jobs. First topic that I am going to discuss in fluid mechanics. So here are the list of the topics you can see. First topic is properties of fluid. What is the basic definition of fluid is the material that do not have any shear strength. It may be a liquid form or vapor form. It doesn't have any shear strength. That is the basic definition of fluid. Apart from this, the definitions like what is density, what is relative density, what is specific gravity, all these definitions also you have to read along with the units. For whatever the definition you are studying, see the units of that also. Okay. Now the first law we will see, that is Newton's law of viscosity. Okay. So what is Newton's law of viscosity means? In solids we have stress is proportional to strain for a solid up to proportionality limit or elastic limit. Similarly, in liquids also we have shear stress proportional to shear strain rate. Why it is shear strain rate means, once we apply shear stress, the liquid will not stop. It will be moving continuously. So we measure the strain rate, shear strain rate. So as we are dividing with time, we will get velocity. So shear stress is proportional to shear strain. There we have Young's modulus as the constant. Here we will have coefficient of dynamic viscosity as the constant. The units of coefficient of dynamic viscosity is Newton second per mm square. Okay. So where 1 Newton second per mm square is 10 poise. Remember this. 1 Newton second per mm square is 10 poise. And when we divide this dynamic viscosity with the density of the fluid, then we get something called kinematic viscosity. So that is kinematic viscosity is equal to nu divided by rho. Okay. So this is measured in Stokes. 1 Stoke is 1 centimeter square per second. If you see centimeter square per second, only kinematic factors are there in this. Dynamics means you should have force. Kinematics means you should have velocity, speed. Only these factors will be there. So if we see the units of this, you will get centimeter square per second, which is nothing but Stokes. 1 Stoke is 1 centimeter per square per second. 1 poise is 0.1 Newton second per mm square. Okay. So that are important things about Newton's law of viscosity. And you can expect some problems also for Newton's law of viscosity. What is the force? What is the force because of the viscosity? So the force can be calculated by shear force. We know what is the shear stress. So force will be shear stress multiplied with area. Okay. Suppose if it is not linear and if it is inclined, if your body is traveling on a slope, this case is also important. So suppose if you have a fluid here, then the weight or shear load that is acting will be W sin theta. Okay. So this slope case you may get, or you may get a linear case, and there is another way you may get a problem, that is by applying torsion. So sometimes between two shafts, when they are rotating, while rotating, one shaft may be rigid and one shaft may be moving. While moving, there will be a fluid between the two shafts. So while rotating, what is the power required for torsion? So that formula is 2 pi nt divided by 60. Okay. So this formula also they may ask. Okay. But for the exams where calculator is not allowed, they may just ask the formula without actual calculation. So at least remember the formula. Okay. Next, these are some standard cases. Suppose if they are copying a question from any standard examination, then you have to see this also. Suppose if there is a body moving like this, I am applying a force in this way to have equal shear force from above and below. Here you have two liquids with the dynamic viscosity nu1 and nu2. If you want to move this bar, to have equal shear force on the top and bottom, the Y value is given by This y is measured from the bottom. If you measure from the bottom, y is given by nu2 by nu1 plus nu2 into h. Okay, the derivation is not required for us, just remember the answer. Okay, next, suppose if you want to have minimum force, to have the minimum force, what should be the y means h into square root of nu2 divided by root 1 into root 1 plus root nu2. Okay, so just in this formula you will have square root, that's all. This is the same formula. If you place square root here, you will get this formula. Okay, so this is for minimum shear force case. Yes, this is for minimum shear force case, and this is for equal shear force on both sides. Okay, so that is one important question. So from Newton's law, you may get a problems like to find the force or shear stress or power like this. Okay, I don't think you will get questions from power, but remaining two, whether it is a slope case or linear case, just to see some problems based on these formulas, that will be sufficient. And remember the units, whatever the definition you are studying, you have to remember units for that. Okay, next, coming to types of fluids, we have two types of fluids basically. One thing is Newtonian fluid, which follows Newton's law of viscosity, and non-Newtonian fluids which do not follow Newton's law of viscosity. Non-Newtonian fluids are classified as Bingham plastic, pseudoplastic, dilatant material, like this. So you can see from the chart between the shear stress and deformation rate, how the shear strain rate is varying with respect to the stress. So that chart is important, but you need not focus much on the types of the fluids. Okay, so that is about the types of fluid. Next we will see pressure and its types. What is this pressure and its type? So what is pressure means, suppose if I take solid can have normal force and also shear force, but a liquid can have only normal force. You cannot apply shear force to the liquid, so it will always have only normal force. So that normal force name is called thrust. Okay, so the thrust creates equal amount of pressure in all the directions. Okay, so this pressure can be represented in two forms. One is absolute pressure, second one is gauge pressure. What is absolute pressure and gauge pressure means, suppose if this is zero pressure and this is atmospheric pressure, this is atmospheric pressure. Suppose if I want to measure the pressure of a point here, I can say this much pressure is there on the for this point, for this fluid, or I can say there is this much gauge pressure for this point. Okay, so I can say this much gauge pressure is there. If you are measuring with respect to atmosphere, you can say in the form of gauge pressure, or you can say in the form of absolute pressure. Okay, so this is called absolute. Okay, similarly, suppose if the point is here, then this will be the absolute pressure, and with respect to atmospheric pressure, if you measure, this is called vacuum pressure. Okay, so vacuum cleaner will have, so you can see how much suction you have. This suction is called vacuum. So if this is below the atmosphere, we measure in the form of vacuum pressure. If it is above the atmosphere, we measure in the form of gauge pressure. Always you can measure with respect to zero pressure, called absolute pressure. Okay, so these are different ways of measurement. Practically mostly we use gauge pressure only. Practically for most of the fluids whatever we have, we always measure with respect to gauge pressure, unless if you have some effects called cavitations and the concept of, when the concept of vapor pressure comes into picture, only at that time we will use this absolute pressure, but most probably in all questions we will use gauge pressure only. So understand this picture correctly, you may get a simple problematic question based on this concept. Okay, so that is about pressure and its types. Next, capillarity and surface tension. Capillarity and surface tension. So in surface tension, the first thing is capillary rise. Capillary rise is given by 4t cos theta divided by rho g d, where d is the diameter of the tube. So theta is the contact angle. We know that. For water the theta value is 0. Okay. And for surface tension, excess pressure inside the bubble, for soap bubble, this is the values of excess pressure. For soap bubble, 8 sigma by d. Sigma is surface tension. Droplet or air bubble, 4 sigma by d. And liquid jet, 2 sigma by d. Okay. So these are the values of excess pressure that we have to remember for surface tension. And also, because of surface tension only, a liquid will always try to obtain spherical shape, because sphere will have least surface area for a given volume. Okay, that is the reason. Next, another important thing, work done in blowing a bubble. Suppose if you have a bubble of radius some r, and if you want to increase the radius of the bubble to capital R, how much work has to be done means, first you have to calculate what is the difference in surface area, that is 4 pi into r1 square minus r2 square. So by finding this area multiplying with surface tension, you can find what is the amount of work done. The soap bubble will have 2 faces, so you will have to multiply with 2. For water bubble you will have only 1 film, so you should multiply with 1. Okay. So that is sigma into 2a, sigma into a. Okay. So these are the important and last, bulk modulus. Bulk modulus in liquids compared to elastic modulus, bulk modulus will give you the more appropriate definition, because it will act per the volume, not for the surface. So that is the reason we will measure always with respect to volume, not with respect to strain. It is not correct way to measure the strain, because the water is highly rigid material. You cannot strain the water so easily. So we measure something called bulk modulus. So we know Young's modulus is stress divided by strain. Here also pressure divided by volumetric strain. So similarly, stress divided by strain, stress divided by strain. Here pressure divided by volumetric strain, delta V by V. That is bulk modulus. Okay. So these are some important definitions that we have to remember. So here we can see bulk modulus units will be, so pressure units are Newton per mm square. Delta V by V will not have any units, so K will have the units similar to pressure. Okay. So like this, wherever you are studying any definition, suppose you see surface tension is force per unit length, so it is Newton per meter, and coefficient of dynamic viscosity Newton second per mm square, and coefficient of kinematic viscosity centimeter square per second. Like this, you see all the definitions and units of the definitions are also very important in properties of fluid chapter. Okay. Topic, fluid statics. In fluid statics, first important law is Pascal's law. What does Pascal's law say is, pressure in all the directions of a fluid element is constant. Okay, so the derivation is not important. The Pascal's law is pressure will be same in all the directions. This is the reason at any height, if you see, you should have same pressure whatever may be the height. Okay, so at every pressure you should have equal amount, at every height you should have equal amount of pressure whatever may be the height. Okay, so based on this principle only the differential manometers are designed. I will just tell you the logic how to solve differential manometer problems, so you can practice the problems or leave it, it's up to you. In order to solve manometer problems, I will just tell you one hint how to solve the problems. In manometer problems, you will have 2 different types of liquids, or sometimes you will have some amount of pressure at sometimes, or you may have different liquids. So suppose if I have, instead of pressure, if I have 2 liquids of this height, let us take. In this case, what you have to do, maybe here also you have another liquid, whatever may be the case. In this case, in order to measure the differential pressure, so here you may have some P1, here you may have some P2. To measure the difference of P1, P2, what I have to do, whatever the liquid that is there in the U, you can see what is the liquid in U. Here, where the liquid, this liquid is ending, there you draw one straight line. Okay, so see what is the liquid here. Okay, so where this liquid is ending, they will give you the height values. So at which point they have represented the height at the end, draw a straight line there. Okay. Don't draw the straight line here, because if you draw the straight line here, you will meet another liquid. You should not do like that. Draw the line here only, so that the line will touch the same fluids in both the sides. Okay. So here entirely you have same fluid, right? So here only you have to draw this. Okay. So after drawing this, now you calculate what is the pressure here, gamma 1 H1 plus gamma 2 H2, whatever you have, and calculate the pressure here, gamma 1 H1, gamma 2 H2, whatever pressure you have. These both pressures should be equal as per Pascal's law. So apply the Pascal's law, equate the pressure, find the difference between PA and PB. Okay. So that is a simple technique I can give you. It works for every case, whatever may be the case. Just you have to identify where you have to draw the line. Okay. So suppose if you are coming from top to bottom, you have to add the pressure. If you are going from bottom to top, you have to subtract the pressure. Okay. So that are different types of problems in manometer. Okay. Okay. Next, Pascal's paradox. What is Pascal's paradox? Means here you can see three types of vessels with same base area. These three have same base area. So these three will have same force, because pressure at any height is same. Because by Pascal's law, pressure at a height is same throughout this length. So all these will have same pressure, same area. So force is equal to pressure into area. So all this will have same amount of force. But this have more weight of fluid. This has less weight of fluid compared to this. So W1 is greater than, W2 is greater than W3. But 3 will have same amount of force. This is called Pascal's paradox. Okay, so which is very interesting. So remember this Pascal's paradox. You may get this in exam. Okay, so remember that. Next, pressure force. What is this pressure force means? Assume this as liquid surfaces. Okay, so here there is a rectangular body. So the centroid of the rectangle will be here, and a pressure force will be acting for me like this, gamma into H. Where will be my center of pressure? At a height 2H by 3, because it is triangle. Okay. So my centroid is here. My center of pressure is here. Center of pressure means where the pressure force is acting, that is center of pressure. So you can see the center of pressure is below the centroid of the section. Center of pressure is below the centroid of the section. Okay. So from the top. Suppose if the body is submerged inside like this, then I will have centroid of this section somewhere at a depth x bar from the surface, and center of pressure somewhere here. Okay, so you can see here also the center of pressure will be below the centroid, obviously. So how to find this centroid depth means, center of pressure depth means, so we'll call it as Cp, which is given by x bar plus I divided by A into x bar. What is x bar means? Depth of the centroid plus I divided by A into x bar. I is moment of inertia of this body divided by A into x bar. So by observing this, you can say, as you are measuring from the surface, x bar plus something means definitely center of pressure should be below the center of pressure, and as this body moves to the bottom, you can see the depth of this x bar value is increasing, which means that this total value is decreasing, which means that as you are going into deep, the difference between centroid and center of pressure will be reducing like this. Center of pressure comes closer to centroid but never meets, because it is x bar plus something. But you have to remember that as we go down, the depth between these two will reduce. Okay, so that is one important bit. Okay, so you may get problems on this concept also. So remember this also. Okay, so remember this also. Next, so that is about pressure, force and problems. Next, metacentric height. Okay. While designing the boats or submerged bodies, the stability of that bodies is measured by a concept called metacenter. I will not explain this, it takes some time to understand metacenter. But for stability, metacenter should always be above the center of gravity. That you have to remember. Okay. So M is always above G, and the length between M and G is called metacentric height, represented by GM. Okay, so this from G, what is the height of M is called metacentric height, where M is metacenter, MG is metacentric height. How to find that means, so from the figure you can see this is center of buoyancy. Where will be center of buoyancy? In the submerged value, if you find the center, that is buoyancy center. For the total body, if you find the center, that is G. So you can find the G value, you can find the B value. For total body center is G, submerged body center is B. You can find BG, but we want M. So how to get that means, you can find what is BM and you can find what is BG. So BM minus BG will give you what is GM. So BM minus BG is GM, where BM is given by I divided by V, that is moment of inertia by volume, will give you what is BM. So by substituting that you will get GM. This is metacentric height. Okay, so remember that always M should be above G for stability. So this is the order MGB. Okay, so that are important points you have to remember in fluid statics. Next topic, fluid kinematics. In fluid kinematics, I don't expect you will get problems from fluid kinematics, but definitions are important. We will see what are the definitions that can come. First we will see what are the types of flows we have. Types of flows is very important in understanding the remaining topics also. So we have to understand what is steady flow, what is uniform flow, what is the difference we have to know first. Then you can understand what is unsteady and ununiform. What is steady flow means the flow that do not change with respect to time. So that is du by dt is equal to 0, you can say. The flow that do not change with respect to time. What does it mean? Suppose if you have v1 velocity at this point and v2 velocity at this point, after certain time if you see, you will have v1 here, v2 here. You need not have same velocity at 2 points, but every time at a point the velocity should be same. That is steady flow. Next, uniform flow means if you have v1 here, here also you should have v1. This is with respect to space. So with respect to space, there should be no change in velocity. Steady uniform flow means, uniform means here and here you have same, and also steady means every time it is the same velocity. Okay, so you understood the difference. So steady means it should not change with respect to time. Uniform means it should not change with respect to space. Okay, now you can imagine what is unsteady and what is ununiform flow. However, the definitions of uniform and non-uniform flows, steady and unsteady flows in open channels is completely different what we study in fluid kinematics. That we have to remember. Okay, so that is about types of flows. Next, lines. What are the different lines we have? First one, streamline. What is streamline means? Line that represents the direction of velocity of a fluid. Suppose if I draw a line like this, it means that at every point wherever I draw tangent, this tangent will give me what is the velocity direction of the fluid. That is called streamline. If I represent all the streamlines of a fluid, then whatever the shape I get, that is called stream tube. Stream tube. And for steady flow, based on the streamline, we will be getting the velocity in the direction of x, in the direction of y, and also in the direction of in the direction of y, and also in the direction of z. This is with respect to x, y, and z. Okay, so from the streamline you can get the streamline function, you can get the velocity. For a steady flow, we should have dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0 for a uncompressible fluid. Okay, we assume water as uncompressible, and dou u by dou z plus dou v by dou y should be equal to 0. When it is compressible, then so actually here you will have density. As it is incompressible, the density will not change, so we will send it to 0. So this is what it remains. Okay, so this is a important equations that we have to remember. Okay, so that is about streamline. Next, second one, path line. What is path line means? Path traveled by a particle. If a particle is traveling like this, then that is called path line. Okay. This is showing the direction of velocity. This is showing the direction of traveling. These two are not same. Okay. For a steady flow, if the flow is steady, it looks wherever the direction of fluid is going, in the same direction only path line is also. It looks like that. But suppose at this point, suppose if it want to turn like this, then the velocity direction will be in this way. Suppose if the fluid that is going here want to turn like this, then at this point the velocity direction is in this way, but the path is in this direction. So velocity direction and path direction need not be same, but if it is a steady flow, then it will be same. Okay. And the third one, streak line. What is streak line means? The flow that is tracked from a common point. What is that common point means? Suppose we are taking one common point here and seeing how the particles are moving. Okay, so whatever the particles that have crossed here, we are tracking with a line called streak line. Okay, so both path line and streak line looks exactly same if it is a steady flow. If it is unsteady flow, suppose if the first particle traveled in this direction, second particle need not travel in this direction. Okay, so what is the path traveled by the particle that is crossed from this point I will track? That is streak line. Here, what is the path traveled by a particle is path line. What are the direction of the particles that have crossed a common point is called streak line. Okay. For a steady flow, streamline, path line, streak line coincides. Okay, that we have to remember. Okay, that is one important bit. Next, acceleration. In acceleration, we will have two types. First one, linear acceleration. Second one is tangential and radial acceleration when it is a rotational flow. Again, in acceleration, we have local acceleration with respect to time and convective acceleration with respect to say space. I don't think formulas are important. Okay, but total acceleration is the sum of local acceleration plus conventional acceleration. Okay, so if you want formula, you can see the formula. Okay. Next, stream function and potential function. Stream function is represented by the symbol xi. Okay, so using this function, what we get? So here you have streamline. This streamline is represented by a function stream function, where dou phi by dou y will give you what is the value of u, minus u, and dou phi by dou x will give you what is the value of e. Okay, so in some textbooks we will see minus for this, and some textbooks you will see minus for this. You can represent for any, it's not a problem. So by integrating this u value with respect to y, I can derive what is phi value, or I can integrate this v with respect to x and I can get what is the phi value. You will have plus c constant which can be derived by using some boundary conditions. Okay. Next, what is potential function? Potential function gives what is the potential head present in the particle. As the potential head reduces along the flow, it is always negative. So dou phi by dou x is minus u, and dou phi by dou y is minus v. Okay, so here you see for x you get u, for y you get v. Okay, so for x only you are getting u, for y you are getting v, but here for y you will get u, for x you will get v, that is reverse. Okay, so remember that difference. So here also you can integrate u to get phi, you can integrate v to get phi. Potential function always follows Laplace equation. What is that Laplace equation? Dou square phi by dou x square plus dou square phi by dou y square is equal to 0. Okay, so this is only for irrotational flow. Okay, so remember, this is called Laplace equation. Dou square phi by dou x square plus dou square phi by dou y square is equal to 0. And stream function and potential function always cross each other at orthogonal. Always cross each other orthogonally. Okay, so that is one important point. And another thing, suppose if these are stream functions and these are potential functions, they cut orthogonally. If you want discharge between two streamlines, dq is nothing but d of xi. Okay, so suppose if you want discharge between 2 points x1 and x2, then calculate phi value at x1, calculate phi value and x2. The difference gives you what is the discharge between the points. Okay, so this is also one important bit. You may get questions on this also. Okay, you can get the questions also in many question banks for these problems, in previous IES questions also. Okay, so that is about the stream function, potential function. Next, vortex flows. In vortex flows, that is vortex flow, you will have two types. One is free vortex, second one is forced vortex. In free vortex, velocity is inversely proportional to radius. Means when you go far, the velocity will reduce. In forced vortex, when you go far, the velocity will increase. Free vortex means without applying any torque, it will rotate by itself. Forced vortex means by applying torque we will rotate, like washing machine. In washing machine we apply force to rotate. If you observe sink and wash basin, if you turn on the tap without any force, it will rotate by itself. That is free vortex. In free vortex, velocity is inversely proportional to radius. In forced vortex, velocity is directly proportional to radius. And what is the depression in forced vortex means? Suppose if you have a bucket like this, and when you rotate this with a rotational velocity W, then what is the height of the depression you are going to get? Okay, so that height value is given by, so assume this as v square by 2g, where v is r into gamma, gamma into r. Okay, v square by 2g. So that is gamma square r square divided by 2g. Okay, here what is the volume of the water that will go out is half of this cylinder, whatever the cylinder you have, half of the water. This is a parabola curve. Remember, this is a parabola curve, and half of the water will go out. Okay, so when you increase the velocity continuously, maximum half of the bucket water can go outside. Okay, this remaining water will never go outside. Okay, so if you continuously increases, maximum half of the water from the bucket can leave. Okay, so you can calculate the height by using this formula. Okay, r into w whole square divided by 2g, where maximum height is height of the bucket. Okay, so that is about vortex flows. Important thing, we will have something called radial flow. In radial flow, the flow will be radial like this along the radius. When the flow is outward like this, it is called source. Similarly, when the flow is inside like this radially, then it is called sink. Okay, source, sink. In our home also we will have sink in the kitchen. So in sink you will have inward flow, in source you will have outward flow radially. These are called radial flows. Okay, and rotational velocity. Rotational velocity formula is not important, but when can we say rotational velocity? If the velocity with respect to mass center of the fluid is not equal to 0, then only we call it has rotational velocity. Means if a single particle has a rotation, we don't say that it has a rotational velocity. With respect to the center of mass, if it has a rotational velocity, resultant rotational velocity, then only we say it has rotational velocity. So you can see the formulas of rotational velocity along x, y, z. I hope you will not get any question from that. Next topic, fluid dynamics. Okay, in fluid dynamics, the important theorem is Bernoulli's theorem, which gives that the total head, the sum of all the head is always constant. That is P by gamma plus V square by 2G plus Z is constant, where P by gamma is the pressure head, V square by 2G is velocity head, and Z is datum head. So the sum of the head is always constant in a pipe flow. So in understanding the different types of instruments, and also in understanding laminar flow, pipe flow. For everything you have to know what is Bernoulli's theorem. Okay, you may get a problems on Bernoulli's theorem also, and where P by gamma plus Z, the sum of these two is called piezometric head. Why you will understand once you see what is piezometer in instrument. And this is called dynamic head. These two are static head and this is dynamic head. This is also known as piezometric head. This is pressure head, velocity head, datum head. Okay, so sum is constant means, so if the pressure reduces, the velocity will increase. So wherever the pressure is high, there the water will be flowing slowly. Where the water is flowing with high velocity, their pressure inside the water will be less. So that the sum of total energy represented in the form of head, this is called head. Energy is represented in meters called head. So the sum of all the energy in a pipe flow, in any flow is always constant. Even in open channels also we use the concept of Bernoulli's theorem. Okay, for all the types of flows like laminar flow, turbulent flow, for pipe flow and open channels, everywhere we will be using Bernoulli's theorem to analyze the flows. Okay, so that is the basic theorem important in fluid dynamics. Next important topic, force due to Z. Okay, so Z of water. Suppose if the Z of the water has the cross sectional area A, then if the Z is coming in X direction, force along the X direction is given by rho A V square. Rho is density of water, A is area, and V is velocity with which it is moving. Okay, if this plate is fixed, then rho A V square. If the plate is moving, then you have to take relative velocity here, that is V minus U, where U is velocity of the plate, moving plate. Okay, so rho A into V minus U whole square. So that is about vertical plate. Suppose if the plate is inclined like this, inclination theta, then the force, then you will have force along X and also force along Y. Here you do not have force along Y because the fluid will not have any shear force. So here force along X is rho A V square into sine square theta, and force along Y, so the same formula, rho A V square into sine square theta, and force along Y is rho A V square into sine theta cos theta. Similar to here, if it is moving, then you will get V minus U in the place of V. Okay, same formulas, V minus U you have to replace if the plate is moving plate. If it is rigid, you have to take V. Now, as this is inclined like this, more water will come this side. So Q2 is Q by 2 into 1 plus cos theta, Q1 is Q by 2 into 1 minus cos theta. Okay. So apart from this, you have curved plates also in syllabus, but as you within the less time you will forget formulas if you read more. So I think with this it is sufficient about force due to Z. And again, there is something called moment correction factor and kinetic energy correction factor. It may be difficult for you to remember the formulas. At least remember the standard cases. How it came, you have to study the concept, variation of velocity in laminar flow and turbulent flow. So if you are not studying laminar flow and turbulent flow, at least remember these values. Okay. So for laminar flow, momentum correction factor is 2, and kinetic correction factor beta, this is alpha, this is beta, is 1.33. For uniform flow, both are 1 and 1. At least remember these values, or you can just see what is the actual formula to calculate this. You need not know the derivation, but at least remember the standard value for this. Okay, so that are some important things in fluid dynamics. Next, coming to instruments, one of the important topic. First important instrument is venturimeter, where you have throat here. In the pipe, there we place a throat in order to calculate what is the discharge. The discharge can be found out by getting the pressure difference through differential manometer. So at the throat, how much pressure difference is getting because of presence of throat. Based on that, we can calculate what is the theoretical discharge, that is given by A1 A2 square root of root 2h divided by square root of A1 square minus A2 square. So A1 is before the throat area, A2 is the throat area here. So by substituting this, we get theoretical. Whereas to get the Q actual, it has to be multiplied with coefficient of discharge. coefficient of discharge is always less than 1. So Q actual is always less than Q theoretical. Okay. Another way of measuring is through orifice. This is called vena contracta. Okay, you will have an orifice here. So from this also you can find what is the value of discharge. So the formula is exactly the same. Q theoretical A1 A2 square root of 2GH divided by square root of A1 square minus A2 square. So here also we will be using a manometer to calculate the head difference. Okay. So as there is more velocity here, you will have less pressure here. So the the mercury will go to the top in order to compensate, so that you will have same amount of pressure here. So here you have more pressure, here you have less pressure, so that the total pressure is same at both the levels. Okay. So this is how we have to solve the differential manometer, as I said. So here whatever the liquid you have, there you have to draw a straight line, you can get what is the pressure difference. So here directly you can get what is the head. After substituting we will get what is the theoretical and actual discharge. Okay. So that is about venturi meter and orifice meter used to find the discharge of the fluid. Okay. So these are used to find the discharge. And next, pitot tube. What is pitot tube means? It is used to find the velocity of the fluid. So pitot tube looks like this. Okay. So from this the velocity is given by V is equal to CV into square root of 2GH. So whatever the head, whatever the height of the head, that is right from the pitot tube. So by multiplying with a coefficient of velocity CV, you can get what is the velocity. So with this velocity, after hitting, if it has risen this much height h, then the velocity will be given by CV into square root of 2GH. Okay. So it is similar to, suppose if you throw a ball upward, how much height with how much velocity it goes is square root of 2GH. If it travels h height, what is the height you calculate? V square by 2G. So V will be square root of 2GH. So similarly, if it is traveling this much height, it should have this much velocity multiplying with coefficient of V, CV. Okay. So that is about pitot tube used to find the velocity of the fluid. Next, most important, piezometer. What is piezometer? Used to find the piezometric head. So if you remember what is piezometric head, P by rho G plus Z plus V square by 2G. This is dynamic head. This is piezometric head, as I said. So if you place a piezometer like this, you will get what is P by rho G plus Z, but not V square by 2G, because here you are not stopping velocity. If you place piezometer like this, so pitot tube like this, you will get velocity. But if you simply place a piezometer like this, then you get P by rho G plus Z. So wherever may be the Z. Okay, so this is the datum. So here whatever you are getting is P by rho G plus Z. Okay, so along the flow, because of the head loss, the piezometric head will be reducing like this. The line joining the piezometric heads is called hydraulic gradient line. Why we call it as hydraulic gradient line means, here you can see it has a slope. Slope means gradient. What is slope here? What is slope? Y2 minus y1 by x2 minus x1. So here this is the origin. So what is the value of y? Nothing but head loss divided by length. Okay. So the gradient is head loss by length. Okay. So this has a different name, as this is the loss in the water. We call it as hydraulic gradient, which is given by head loss per unit length. Okay. So that is called hydraulic gradient. Suppose you find the total energy by combining V square by 2G, then you get total energy line. But this do not have any significance for us. It is not useful in pipe flow. But HGL is very useful in analyzing the pipe flow to see how much pressure is there inside the pipe, to analyze whether there is any cavitation occurring inside it. So whether minimum pressure is maintaining in the water or not. So to analyze all this, HGL is very important. So apart from this you also have to know about notches. You may or may not remember the discharge of notches, but you have to remember two things in notches. One is, for a rectangular notch, Q is proportional to h to the power of 3 by 2. For a triangular notch, Q is proportional to h to the power of 5 by 2. And you have trapezoidal notch, where we combine rectangle plus triangle to form a trapezoidal notch. But you have to remember that rectangle Q is proportional to h to the power of 3 by 2. Triangle Q is proportional to the h to the power of 5 by 2. In solving some problems, they may ask you a question like, with respect to change in head, how much Q will change? So here if you differentiate this, you get 1.5 times. Means Q will change 1.5 times if you change the head. Similarly, Q will change 2.5 times if you change the head value with respect to Q in trapezoidal notch and triangular notch. Okay. Notches are also used to find the discharge in channels. Here the discharge in pipes. So discharge in pipes can be found by venturimeter, orifice meter, and velocity in pipeline it can be found by pitot tube, and piezometric head can be found by piezometer, and discharge in channels can be found using notches. Okay, notches and also weirs. Okay, so that are some important instruments that we have to remember. Okay.